My name is Anna Meadows. I am a volunteer coordinator for the Springfield Community Gardens. Thank you to everyone who's here tonight. We're going to be talking with Adam Millsap about packing sheds. Before you get started, if you do have any questions throughout the night, feel free to put them down in the Q&A section below. There's a button at the bottom of your screen that says Q&A. You can click on that and type your questions there. We'll be taking questions periodically throughout tonight. If you could put questions in the Q&A chat instead of the chat button at the bottom, that would be helpful for me. But feel free to put any comments you have throughout the night in the chat section. Yeah, that's really it for me. Adam, welcome. Thank you for being here tonight.
Thanks, Anna. I think not really what we had in mind when we originally started talking about this. Building a pack shed and a do-it-yourself cooler might be better served by hands-on experience, but obviously that's not possible right now. So we're going to do the best we can tonight. We'll talk a little bit about the pack shed design and the way we thought through that. But for the most part, we're going to focus tonight on building a walk-in cooler in a do-it-yourself way. So I'm going to start with a couple of goals. We'll talk through the goals of why we do this kind of work ourselves on the farm and why we self-design and self-build things like both the pack shed and the cooler. And we're going to watch a couple of videos. I think we'll watch the first video, which is just talking about the structure that we built for the cooler. And then we'll talk through that and those considerations. And then we will talk through we'll watch the installation video and talk through those considerations. I want you guys to get what you came here to get out of this evening. So if you guys want to guide the conversation to some degree, I welcome that. My preference for these kinds of conversations is exactly that, for them to be a conversation among folks who have knowledge and folks who are seeking knowledge. So feel free to guide that conversation. So our goals as far as self-building these types of things and self-designing these types of things, our leading goal is probably to make it affordable, to make it inexpensive. And if that wasn't a goal, and if that wasn't a desire and a necessary desire for small farmers, then certainly we would all hire architects and builders to accomplish these things for us. And if that's in your budget, I certainly encourage you to do that. But we'll talk tonight about how we can accomplish these things ourselves. We want these things to be practical for our purposes. We need them to be easy to work in and around. We need them to make sense for the things we do on the farm. And nobody understands those things better than the people who are doing them. So there's some benefit there. We want it to be laid out for the way we store things and the way that we move through those spaces and the way that we move things. So it's very beneficial to think those things through before you get too far into this process. If you're not already doing them, if you're pre-planning for a project, then really thinking that process through. Spaghetti diagrams can be really helpful, which means that you get your layout and put it on paper, and you start drawing the way people move through that space and their cycles through that space, and start thinking about how things might move in order to reduce the length and the overlap of those cycles. We want these things to be durable for our uses. Washing vegetables is a messy, wet operation, and we need to choose appropriate materials for that use that'll last us a long time. We want to be efficient in those spaces. I mentioned that, but that's a really big one, thinking through the efficiency. And we want to plan the projects out before we start building them. We want to have a really good, solid plan before we get too involved, which saves us money and gives us predictable and manageable timelines. And the most important thing that we want to receive from these structures and these endeavors is farm efficiency and farm profitability, which in my way of thinking are almost always the same thing. And in the end, we want to deliver a fresher product, the freshest product that we can to our customers. So the SCG pack shed, Melissa and I worked on the design of it together. And we've designed 3 or 4 pack sheds at this point that have been built. And we almost always start with a floor plan. We don't start with a specified size. So we don't say, this is going to be our footprint. How do we fit everything in here? We don't say, this is what the building's going to look like. And how do we make everything fit in there? We start with what Melissa likes to call her Barbie house, where she and we cut all the little pieces out to scale. All of the equipment that we know we're going to need in that space is cut out to scale. And then we begin arranging it and organizing it with site considerations taken into account. So some of those site considerations may be which way the sun's going to hit this building. That informs where our windows are going to be, and our windows can inform what kind of equipment might go on those walls. We're going to consider if there is any slope involved. For instance, at the Urban Roots wash shed, we had a pretty good grade where we put the building, and so we had about 3 or 4 feet of grade change from one end of the building to the other, and we were able to take advantage of that by giving ourselves a little loading dock on one end that we can back our truck up to, and either load produce and whatnot into, but also load equipment for the farm or equipment that we borrow from other farms on and off, which is really great. So you do want to think about those grades, how that's going to play out, and how your foundation and your slab needs to be poured in order to accommodate those grades. So site conditions may dictate to some degree, but mostly the way you're going to move through the space is going to dictate that. Where your doors go, how you flow through the building when you're bringing produce in and produce out of the building certainly plays a role in that layout too. Very important to give yourself clear pass-through pathways in addition to the pathways and the spaghetti diagrams that are going to happen when people are actually working and preparing produce for market in those spaces. So all that said, I consider probably the most important feature of our wash and pack sheds to be our walk-in coolers. They can also represent a really large portion of the cost of those structures. And I say that because not all of us are going to build what we might traditionally consider to be a structure or a building for our wash and pack shed. They run the gambit from pretty significant structures to a concrete pad in the end of a high tunnel where production may be taking place in the rest of the high tunnel. Of course, what you're allowed to do along those lines will vary depending on what regulatory agencies are involved in where you're siting your farm. So, depending on what county you're in and what municipality you're in, you may have more or less freedom as far as how you design that space and how significant that space has to be. But certainly an inexpensive way to get a pack shed space on the ground is to build it inside of a tunnel. And I will say too, real quick, this was something that we didn't think through a lot when we started Urban Roots 10 or 11 years ago. And for that reason, we spent 2 or 3 years washing produce in a 3-batt sink that was against the north wall on the exterior of our greenhouse. And that meant at a 4-season farm, as you can imagine, that we were washing produce in 105-degree heat in the glaring sun, although we did put a tent up occasionally back there. In the summertime and in the wintertime, we were up to our elbows in near freezing cold water. We did find some really great insulated rubber gloves that helped us out with that. And if it was pouring down rain, we had that tent up, but we might have been in ankle deep water standing around back there. So, and it was a real Achilles heel for the farm. There was today I think of the wash house and pack shed as kind of the neural center of the farm. It's where we handle a lot of planning. It's where we keep task lists. It's where morning meetings happen. And it is where produce flows off the farm. And so it is really critical to have a well thought out and efficient space. I also encourage people to reuse as many materials as they can. I'm a real scrounger, real scavenger. I was just giving a tour of our pack shed at Urban Roots to a fellow the other day, and he walked in and he goes, this structure is not meant for this, is it? And I said, no, it's an old carport that we repurposed. And the reason he was looking at that is because it has some very significant I-beams in it that are way oversized for our purpose. But what that meant is that we got our entire roof structure free of charge by disassembling it and repurposing it. Our walk-in cooler at Urban Roots, the insulated panels came from El Chico. I don't know if any of you remember El Chico in the Battlefield Mall parking lot, but we were driving by one day when they were preparing to demolish that building, and the walk-in cooler was still there, and we were able to snag that. We were out there till about 2 a.m. disassembling panels. So yeah, all the windows in our pack shed are actually commercial doors turned on their side. So yeah, lots of materials available if you keep your eyes open, and that's a major means of cost saving at our farm. Of course, I suppose that all depends on how you value your time as well. But as I said, cold storage is a really critical feature on a farm, and again, that's something else that we didn't realize when we were starting our farm. We didn't realize how important that was, and what a big difference it made in our task flow on the farm, and what a big difference it could make to the freshness of the produce that we were delivering to our customers. Years ago, we went to a conference in St. Joseph, Missouri. I think they call it now the Great Plains Growers Conference or something like that. They changed the name a couple years ago, but the keynote speaker that year, one of his favorite statistics was that for every 10 degrees Fahrenheit that we reduce the temperature of a piece of produce, we are reducing the amount of biological activity in that piece of produce by half. And as you probably know, once we've harvested that produce, that biological activity is decomposition. And so for every 10 degrees Fahrenheit after harvest that we decrease the temperature of that produce, we are diminishing the decomposition that's happening in it by half. And so when I heard that number, it was pretty shocking to me, and it really changed the way I was thinking about things. And then the other thing that he said along with that was that oftentimes, although farmers marketeers will often sell their wares as the freshest available because they're the most local available. And that was certainly what we were doing. That was certainly the way we were thinking. The reality was that oftentimes, biologically speaking, the produce that our customers were buying at a grocery store were fresher than the produce that we were offering them at farmers market that we had harvested the night before. And the reason for that was because our produce was going in a cooler with ice blocks, which is not a very efficient way to cool produce. Whereas California produce was being harvested in the field, put in boxes and put in a refrigerated truck about 45 seconds to a minute and a half after it was cut off the ground. So, and the supply chain allows for it to be refrigerated from the field to the grocery store. So it's something really to consider if you don't have cold storage as part of your operation, or you're not planning cold storage as part of an operation that's forthcoming. You should be. So that said, we are going to talk a good deal tonight about cooler design and cooler construction. There was a couple of videos that were made as we constructed the cooler at SCG, and we're going to watch those videos right now, and then I will probably pause them a couple of times as we come across bits that need a bit more explaining or benefit from a bit more explaining. And certainly if you guys will chime in with questions as we go, then we'll get those answered as well. And then when the structures video is done, we will we'll talk through some of that stuff and some of the considerations when you're building the structure for a cooler. And then we'll move on to insulating a cooler and all of the considerations that go into that. A minute ago when I tried this, it didn't immediately play the video, although it played the sound. So do please let me know if you guys don't see the video.
You don't see the video yet.
Not on screen yet. Well, let's see what's going on with that. Oh, Anna, we even tested it and now I can't make it happen. Let me give it its own screen and see if we can work it that way.
Oh, it's coming up. There it is.
All right. Let me know if you've got sound or not as well.
Of the construction of... Hey, I'm Adam with Urban Roots Farm, and we're going to be shooting a video of the construction of a pack shed cooler, cold storage for a small vegetable farm here with Springfield Community Gardens. So we're going to be running through the basics. Obviously, we've already started construction here. We're going to run through what we did today, and now that we actually know what we're doing, we're going to let you know what we're doing. So basically, the style of cooler that we're building is going to be an exoskeleton structure with insulated interior walls. One of the main principles that go into designing a home-built cooler is you want to absolutely minimize the amount of thermally conductive material that is running from the inside conditioned space to the outside space. If we were to put our cold side on this side of the stud and just put a piece of sheetrock out here, what we would see is wetness along that sheetrock, because this joist would transfer the cold from the inside of the cooler to the outside of the cooler.
So can you guys hear me now?
Yes, we can hear you.
Okay, great. Thank you. So I didn't do a great job of explaining that on the video when I said that we were going to put the cold side on the inside and warm side on the outside of that stud with a piece of sheetrock. But this graphic does a bit better job of explaining what I meant, which is really that if we just put the insulation between the studs, and then we have our cladding on the interior of the cooler and our cladding on the exterior of the cooler, both in contact with that stud, whether that stud is metal or wood or whatever conductive material, and wood is more conductive than we would probably think of it offhand, then we will see sweating because we're going to see thermal transfer through that stud from one side to the other. So we're going to get sweating on the exterior of the structure
because it's not very insulated. So, but the way we're going to do that today is to build the frame outside, and then all of our insulation will go on the inside, just hanging off of that on the walls and on the ceiling. Additionally, the way we chose to construct this is basically like a deck construction. So our ceiling is freestanding and is supportive structurally. We want that because we're going to use the storage space up there. We don't want to waste that. Obviously, just this wall holds up all of that deck up there. And then the wall that we'll build in here tomorrow will just slide into that space and get tacked in place. Won't really do it.
So in case that wasn't clear, basically the wall that I'm standing next to here is the structural wall. It's the one that's holding the roof up, the ceiling up, in combination with the existing wall of the pack shed there that we put our ledger board along over here. And then the wall that fills in here that'll contain the door is not structural at all. It's just popping in there.
Structural work. Our pad is insulated, and this is really critical. These are thermal breaks, and you can see that we had to cut ours out because we accidentally poured our concrete before we got our thermal breaks in the floor. But they are so important that we cut this out and broke our pad out and put them in. We have 4 inches of rigid foam insulation, giving us about an R20-ish value. Laid on the bottom of the pad, so the pad is poured on top of that. There's a wire mesh in the pad as well to reinforce it. And then around the edges of that 4-inch foam base, there's a thermal break. And that thermal break is made up on the sides that we don't have doors in of 2-inch rigid foam insulation, and on the side that we do have doors on by 2 inches of redwood. So when we chose that wood because it's not going to rot if it gets a little damp down in there.
And again, wood is conductive, so it's not a complete thermal break, but it's a lot better than concrete in direct contact with itself.
Roll our carts in and out of here, we need a hard surface to roll over here. And if we had the foam there, it would eventually wear the foam down and break into pieces. So, but the takeaways there are, it is absolutely worth insulating your floor. The amount of energy that you lose through the floor is enormous. So if you do not have an insulated floor, if you can't build an insulated pad, I would encourage you to go ahead and put a floor in your cooler, just rigid foam with plywood over it, and build a ramp into it. It is that critical. It's really, really important. Otherwise, your temperature will never hold in your cooler, no matter how big of a cool bot or a cooling unit you throw at it, because that cold air is just, the cold temperature is just running right through your floor into the ground underneath. And the ground can sure suck up a lot. So very important to get your thermal break in and get your insulation in underneath your pad. If we didn't have the thermal break here and we had insulated the pad, what you'll see is the floor will get very, very wet all around your cooler all the time, which also means that it's sitting very, very wet under your wall, and it's eventually going to rot it out. So the thermal break is also really, really important.
And something else to note right there is you notice that the plate on the floor is greenwood. It's treated lumber, and the studs that are running upright are not. And that condensation is exactly the reason, as well as just general wetness in a pack shed scenario. Anything that's in contact with the floor is going to be greenwood, treated lumber that's rated to get wet.
Okay, so the type of construction we're doing here is pretty standard stuff. For instance, we used the joist hangers over here along this ledger board, ran our rim joist into the wall over there. So pretty standard stuff. We're really not doing anything out of the ordinary, and it's really not specific to the construction of our cooler. There is literally 1,000 different ways you could build this exterior box to hang your insulative material on the inside of. So we're really not going to go into too much depth on that. There's lots of good resources out there for how to build a box.
Okay, so that is our structure video, and we can go into as much detail about building the structure as you all want. Even though we said we wouldn't in the video, we will here. And that's, I think, what is probably evident in that video is that it's really, really critical that we have an insulated base. And so that's something to be thinking about as you plan your pack shed in general. Is, if you have an existing pad, then clearly you're not going to be able to insulate the pad under the cooler. And like I said, we had some communication issues that led to our concrete pad getting poured before we got insulation under the cooler space. And so we went to great pains to cut that out and jackhammer it out. And that's how strongly I feel about having your cooler on an insulated pad. If that's not possible, as I said, you can always, put insulation down and put a plywood floor over the insulation. Something to be aware of there is that insulations come in various densities, even expanded polyester insulation like we're using in the video. It comes in different densities, which have different PSI ratings. And so you're going to want a fairly high PSI rating for an insulation that's going to go under a floor that you're going to be rolling carts around on and whatnot. So that is a consideration there. Anita asks if we would use heat-treated lumber. I'm not real familiar with heat-treated lumber, so I couldn't say for sure whether or not I would. But the simplest way to answer that is probably that we need to use a lumber or a material that is rated for rot resistance in an environment where it's going to get wet and dried. So some of those that come to mind right away is you could use cedar or redwood like we used in the floor, or the easiest and least expensive option is treated lumber. You would need to check if you're certified organic. You would need to check with your certifier about that. But as far as I know, you're okay to use treated in construction that's not in soil contact. So let me get my notes back up here real quick. Too many screens going on here. So yeah, and you can lose up to 60% of your thermal energy through the floor if it's not insulated. So even though it's a pain, and if you have to build a floor on top of your pad, an insulated floor on top of your pad, and need to put a ramp in or have a step up, it's worth doing that and dealing with that. But if we're planning really well from the start, that really shouldn't be the case. We should be able to have a same level insulated pad that will serve that purpose. So You may have also noted that the structure, the ceiling structure in that cooler was heavier duty material than the walls. And the reason for that was because we wanted to be able to use the space above it for storage. And so we beefed up that structure on top, and then we ended up putting a plywood floor up there. So we have shelf storage on top. Does anybody have questions about the basic structure there? All right. If you do, just pop them in there and we'll get to them. Some things to consider about what type of structure you choose. Like I said, there's 1,000 ways to skin that cat. And so I can't tell you how you're going to do it. And I can't tell you how you should do it. There are lots and lots of ways to go about that. And like I said, at Urban Roots, we were able to salvage a old walk-in cooler and make up use of that. And so that was both our structure and our insulation. Of course, you can always buy walk-in cooler panels as well. Even Coolbot is now selling walk-in cooler panels. They recently purchased a manufacturer of walk-in cooler panels, and so they're selling them along with their units now, if you want them. Some folks, you may be building a standalone walk-in cooler. If that's the case, you're likely to build more like a shed, and then insulate the inside of it. Certainly something to think about as you are designing your cooler space is that because of that desire to isolate thermally conductive materials, we're always going to be insulating to the inside of our finished structure. And so your box can get really small if you buy lumber materials to build, say, an 8x10 cooler, and then you put 4 inches of insulation on all sides of it. You've significantly reduced the interior space of your initial structure, and so that's something really to take into consideration as you plan. Is you want to oversize the structure so you get the right size box when you're all done. Yeah, we need to, of course, protect the cooler from weather. So, and that's true whether you're buying a walk-in cooler or building a walk-in cooler. You're going to need to build some kind of roof structure on it if it's going to be exposed to the outside. Dwight asks, what about an air gap for thermal transfer? And that is a good question. Air gaps are somewhat effective, but we do still get a lot of convection in those spaces, and we can get radiant transfer through those spaces. And so unless we're dealing with vacuum, we're really not going to have enough of a insulative value in an air gap to meet the requirements of a space that we're going to keep that cold. We could throw a lot of energy at that and not get it cold enough. But that's a good question. Certainly in our greenhouse, we use an inflated plastic, and that does have a significant impact on our heating costs in there. But yeah, like I said, something that has a higher R value is going to be required for a walk-in cooler scenario. And in fact, the industry standard for walk-in coolers is R25, which is really quite high. And that's the EPS foam that we're using in this video has an R value of, depending on the density of the foam, somewhere between 4 and 5. 4 and 5 R factor per inch. And so in a 2-inch foam panel, you're going to have anywhere from 8 to 10 as an R value. And of course, we're stacking those, and as you stack them, you increase that R value. Yeah, and those thermal breaks, like I said, absolutely critical. And in case that wasn't clear in the video, the way that pad was constructed is, it's basically, if you think of just a square sump in that space, and at the bottom of the sump, we have a couple of panels of EPS stacked. And then along the edges of that stacked EPS, this runs all the way out to the edge. And then our thermal break comes down and sits to the inside of it. And that's sealed to that, because even with our concrete sitting on top of that pad and up against our thermal break, the thermal energy is still traveling through that pad, and it's going to want to seep out those cracks and find its way into the ground. So we do seal that as well inside there before we put concrete over it. Yeah, you need to plan your insulation that is appropriate for your conditions. And something that we learned at Urban Roots after we put our walk-in cooler in is that in our area, we don't heat our pack shed in the wintertime. And so we get some solar gain when the sun's up, and we designed it, and this is a good design consideration, we designed it to be passively heated, just with an overhang that shades us in the summertime and shades those windows. And then in the fall and winter, when the sun is low, it penetrates those windows, and we get that heat gain inside. So it's pretty comfortable on a sunny day. But at nighttime, ambient temperature around that cooler is whatever the ambient temperature outside is. And so if we're getting down, like a couple weeks ago, really cold, it's very, very plausible that our produce will freeze inside of our walk-in cooler. And so we run a heater inside the walk-in cooler in the wintertime as well, set up on a thermostat that just keeps it just a little bit above freezing. So yeah, and Dwight's saying spray foam provides a much higher R value. Yeah, because spray foam seals all air movement, it is a very, very effective product for this. And if you are up for DIY spray foam, it's a pretty good option. It is comparable in cost per square foot, and if you're doing it yourself. If you're hiring it done, it's somewhat more expensive. And the downside is it does take some expertise, and there are some potential indoor air quality issues if it's not done well. So something to consider there. It can continue to off gas if it's not well installed. So I think we'll go ahead and jump to the insulation video here, and we'll watch that and talk through that, and then we'll get into the nitty-gritty of that afterwards. I have to tell you guys, this is very strange. I feel like I'm sitting here talking to myself.
You're doing a great job. Very interesting.
Just sitting in a room talking to myself about walk-in coolers, like usual.
Andrea says, we are listening.
Great. All right. We have video up, Anna?
You can see it. Yep.
All right. Thank you.
All right, so we're getting some stuff figured out here with our cooler build. Just wanted to take a quick second and talk about how we're going to orient our foam board to minimize air movement.
It's probably worth noting the blocket material that you see in the back of this is a vapor barrier that was installed on the inside of the pack shed, and probably not necessary, but it's not a terrible idea to have a vapor barrier anywhere where thermal exchange is going to happen.
Went through it. All our seams should be sealed up either way and shouldn't allow air to flow through, but we want to do everything we can to minimize that effect if that were to happen. So as you can see, I oriented the first set to run perpendicular to my joists, and that's because of the way I want them to line up with the joists so I can have something to fasten them to. But this second set, the second layer of rigid foam, is going to go the opposite direction, and there's two reasons for that. If I had planned my cooler in such a way that I could just use full sheets, which is a great idea if you're planning your cooler.
So that's a really quick little mention there, but boy, could it make a huge difference to your materials use and how much cutting you end up doing in your cooler. EPS foam sheets are 4 feet by 8 feet. And so if you design your cooler, if you are going to use EPS, if you design your cooler to multiples of that 4 by 8 on its interior structural dimensions, you can really save yourself a lot of build time and also waste.
Then I would still want to orient them the opposite way, because if you think about a sheet sitting here and a sheet sitting here, the only place where those seams line up between these sheets and those sheets is right there at that little pinpoint where they cross. Whereas if I run my next layer of sheets this way and this way, the seam lines up all the way the length of the sheet, and that's what we want to avoid. And then secondly, because
So I think that probably makes sense, but just in case, basically what I'm saying is if my fingers are 2 sheets and they have a seam between them like that, and I line the next 2 sheets that are overlapping them up this way, that crack, however big it is going to line up and allow air to flow through cleanly from one side to the other. Whereas if I rotate the sheets on the second course, the only place where those line up is that little bitty slit right through the center. And we're going to make sure we seal that, but we've significantly reduced the amount of space where that can be a problem.
It requires a narrower piece on one end of it. I want to overlap that as much as possible and offset that as well. So if you think about my 8-foot sheet going in here now, it's going to just barely overlap out into the middle of this sheet where there's no seams. So I'm landing my second layer of seams where there are no seams in my first layer. And that's the goal here. Anytime that we're using sheet goods, and sheet goods in general in construction, but especially when we're insulating something with it, we want as little overlap of seam as possible. All right, so this is day 3 of our cooler build here at Springfield Community Gardens. I'm going to take you guys through where we're at and a couple of decisions where we've made and why. So we're just starting to put the foam board on the walls. We've got both of our layers on the ceiling, and we'll talk about how we laid out the ceiling boards in order to avoid cracks, and what we did where we had cracks, and also how we're fastening these things on. So on the ceiling, as our first layers ran this way. So the long side of the foam board was running this way. And we started in that corner with those. Or minimizes the amount of air movement that could potentially happen. And again, remember that if we run our boards, our foam board perpendicular, we just end up with that little pinpoint where those seams crisscross. whereas if we run them parallel to one another and in line with one another, we end up with a seam that runs the entire length of our sheet and potentially allows air movement in and out of our conditioned space and our non-conditioned space, which is, after all, our primary goal to avoid.
Yeah, so I threw in there at the end to avoid. Our primary goal to avoid. So yeah, that's clear. But I do want to say that even on the ceiling, although we think about cold air falling because it's denser, it wants to push down and seeks lower elevation. By eliminating the cracks on the top, we're eliminating the ability for that air to be displaced. And so if we're not pulling warm air in through those cracks on the top because they're not there, then we're also holding that column of cold air that sits in there captive because we're not allowing that exchange to happen.
Over here in the corner, you can see that just because it's pretty unusual for a box to be perfectly square, we will end up occasionally with some very small gaps. And when we end up with those, it's really important that we shoot a little spray foam in those. And you can get your can up there and just barely fill that and let it fill out. And then we can cut that off flush after it sets and before we put our FRP on. We are going to cover all of this with fiber reinforced panels so that it gives a little more durability to it. Obviously, this stuff dings up and chips up really easily, but it'll be very durable with the FRP over it. We also designed the ceiling height of the cooler to minimize the number of cuts that we would have to make once we started putting up our wall panels. So we built our ceiling height before insulation at 100 inches. So that once we had our 2 layers of insulation up there, we end up with 96 inches. And these tuck in really nicely under it. That will minimize our cuts when we put the wall panels up. It also, as it turns out, makes it really convenient to prop these up when they're being glued. And all around the cooler, ceiling and walls, the first layer of foam, we can use fasteners to attach them to the studs or to the joists in the ceiling. But in our second layer, and where applicable a third layer, we won't have any fasteners. And that's, again, because we don't want that thermal energy to be transferring through anything that's conductive. You know, the insulation, the whole job, the entire purpose of it is to prevent that conduction of thermal energy. If we take a steel nail and pop that through there, that's just one little channel for conduction, and we want to avoid that in our first layer.
And what will very realistically happen, and I know this from deconstructing some things that have been built this way, is that nail in that board, the board's warmer, the nail's colder, and that sweat inside that board and cause a rotted spot. And then I also want to be clear that we're not using those nails to hold those panels up there in whole. There's glue on the joists. The nails are just there to hold them there while the glue sets.
We are using 3-inch roofing nails to tack our boards in place. We're also gluing them. And so on our ceiling, we used those to tack it up there. We put glue on the joist before we stuck it up. And then these will lay over and no fasteners will be used. So as we started putting that second layer on and finding that we needed to prop those up while the glue set, this turned out to be extremely convenient because of the dimension. The glue we're using, let me grab this. We're liking this. We started with standard liquid nails, but we were finding that that construction adhesive type didn't have enough early tack to hold our stuff up soon enough. We would have had to leave it clamped up, if you will, for a while. This stuff, it seems that we're able to clamp it for just a few minutes and then pull it off there without anything sagging. So we can move a lot quicker that way. So this is working great. It's liquid nails. Fuse it. I'm sure there are many other brands that offer a similar product, but it's working for us. So yeah, I think that's all about the panel layup, and we'll talk a little bit about the corners as we start putting those together, how we're going to lay those corners up to, again, minimize that potential air movement from the conditioned space to the non-conditioned space. We're starting to put panels in perpendicular to one another here on the wall. And just wanted to take a real quick second to make sure we know that we want to put spray foam down the corner before we push that in, and that will allow whatever variation is in this corner to be taken up as the foam expands out into that crack, and make sure that we don't have, again, air movement through that corner. This layer will go in like that, and then our next layer will come in like that. And at each step, at each layer, we'll have spray foam in that corner before this goes in there, which will allow it to expand out and fill up whatever gap we have. It'll also make for a really rigid corner because that spray foam is quite adhesive on this foam and will make for a very strong corner. Does not.
So again, we're offsetting the way surface is made up. And we're doing that at every step of the way to create as much of a maze and as much of a gauntlet as we can.
Take much in the corners there because the crack that we're going to leave behind is going to be very small. So just like a bead that you would use sealing a bathtub or something like that is all you need. And it'll expand out to fill a larger crack. We're going to butt that really well into the corner before we push it up. And because our floor is rough, we're going to butt it in at the bottom before we butt it in at the top. The top's smooth, it's easy to slide on. The bottom is rough, it's difficult to slide it across, and we'll tear up our foam as we push on it. You can see that it's fighting me just a little bit, which is good because that means we're going to be really snug. We'll take our mallet and a nice wide flat board to distribute the force. And just tap it in there where it goes. We're also going to, not on the first layer, but on our next layers, we'll also spray foam before we stand that wall board on the floor against the wall in order to get a really nice seal at the bottom. Now that we have a nice clean mated corner between our wall panels and our ceiling panels, we'll make an effort to put a bead of expanding foam in that corner before the next sheet goes in. But it's less critical at the top than it is at the bottom. And the reason for that is the same as what we talked about in the importance of insulating our pad. That cold air is heavy. It wants to settle to the bottom of the cooler. It really wants to push through our floor and conduct through our floor into the ground. And anywhere where we have a little crack in the corners, the weight of that cold air is going to want to push it right out of there. So we'll try and seal up all of those cracks all the way around the base of our cooler. So it works like a deep freeze, and that cold air just sits down in it and doesn't have anywhere to go. So we've got a little mistake we made here that we want to address so you don't make the mistake also. We talked about the thermal break earlier and how important it is to prevent sweating outside the cooler and loss of energy through the pad to the unconditioned space. What we didn't think about though is we're using a standard door as our cooler door. If you can get your hands on a real cooler door, this will be less of a problem for you because they're a lot thicker. But these are a lot easier to get a hold of and certainly less expensive. As we laid out our thermal break, we needed to give a little bit more thought to the shape of our door jamb and where the door actually seals to the floor. As it stands right now, when the door is closed, of course it comes across this side of the jamb and it seals against the floor about 3 inches to the outside of our thermal break. And what that means is that this 3 inches is going to be sucking up cold energy, thermal energy, out of the cooler and transmitting it into the pad out here. I don't think it'll be a really critical problem in this very small space, but it would have been something to avoid if we could have. So it would have been better when we laid out our thermal break to really plan where our door was, get it drawn out on the floor, and lay out that thermal break so it followed the shape of the door and avoided that problem. Should have come out back here where it's still under the insulation, out into the doorway, and optimally directly under the door is where it would end up falling. So lesson learned. Of course, to be honest, I don't think even if we had put in our thermal break before we poured our pad, that I would have thought to do that. So here's your opportunity to do so. But certainly it would have been very difficult with the pad being cut out and poured out to have executed that shape in an existing pad. So hopefully you don't make the same mistake. Here's your warning and your opportunity to get your thermal break under your door.
Adam, we can't hear you. Can't hear you. Nope.
Can you hear me now?
There you are.
Right.
Very good.
My other headset died while we were watching the video. What I said there at the end, this is your opportunity to not make the same mistake as me. That's what we're doing here, right? Is you are learning from my mistakes. So try and be as honest about those as we can be. That said, I certainly still don't have it all figured out. So please don't take things we're talking about today as the say all end all. If you have better ideas, use them. All right, so I'm sure you guys saw again, the biggest things we are working on in this design is reducing airflow, air movement from inside the cooler in the conditioned space to the non-conditioned space, as well as reducing convection. And we accomplished that convection reduction through our insulation, and we accomplished that air movement reduction through good sealing and good layup design. So like we were talking about in those corners where we're stacking those corners, and then the ceiling running perpendicular. Can't read and talk at the same time. Sorry guys, I should probably finish saying what I'm saying before I read questions. Rick is asking if we can attach shelves to that type of wall. I would not recommend attaching shelves to that wall. The only way that you could safely attach shelves to that wall would be through the insulation into the wall studs, and that would mean running a fastener through your insulative barrier, which would negate its purpose. So can't recommend that. To take that question one step further, the type of shelving that we use in our pack shed, in our walk-in cooler, is always freestanding. So it doesn't require that fastening to the walls. And then Nathan's asking if we removed the nails from the joists on the first layer insulation. No, we did not remove them. Because we have another layer of EPS foam over that, I'm not concerned that that nail is going to conduct enough thermal energy to result in that rotting and that sweating effect in the joist or in the stud. Not too overly worried about it because it's beneath a layer of insulation. So the amount of difference between those thermal layers plays a large role in how efficiently they transfer energy. So so for instance, if that nail is in a 30-degree space and that stud on the exterior of the box is 75 degrees, it transfers a lot more energy than if it's behind a layer of foam where the temperature is, say, 45 or 50 degrees, and it's transferring through that next layer into the stud. So not too concerned about that. Although if you were determined, you certainly could remove them, and that wouldn't hurt anything by any means. So yeah, the EPS foam, I mentioned before that it comes in different densities. If you are building a floor on top of a slab, that's something to really take into consideration. And you may have to look around a little bit to find higher density and therefore higher PSI rated foam. But I do, if you're putting it in a floor, even with plywood over it, recommend seeking out that higher PSI foam, because I do think that running the same path over that foam, even with plywood on it, will slowly but surely degrade the structure of it, and it will begin to come to pieces on you. Things will start moving. Something else to know about EPS foam. There are definitely environmental impact considerations when you're using any foam products, but particularly EPS, because EPS, there are still hydrofluorocarbons used in the production process for EPS. There's a fairly strong argument made that because of its efficiency, the offset in greenhouse gas production through reduction of energy use is enough to justify it, but it's really something to think about. EPS manufacturers are going to be required to stop using hydrofluorocarbons. I don't remember, it's in the next 5 years, but I don't remember the date. So that's something to keep an eye out for too. There are alternative products, but they generally run quite a bit higher in cost as far as the amount of R value you get per dollar per square foot. And flooring wise, I wouldn't use anything but EPS. Walls, you could probably get creative and use some other products if you were so determined. Mentioned that EPS has an R value between 4 and 5 per inch of thickness. So that's something good to know. And then the industry standard for walk-in coolers is R25. And that is a lot of R value. Certainly, if you can afford it in your build, it's not a bad idea to get that much in there, and you could accomplish that with 2 layers of 2-inch and a layer of 1-inch. If it doesn't fit into your budget, and I should say the EPS is one of the more expensive components of this. Your insulation in general is one of the more expensive components of a build. If it doesn't fit into the budget, then I have found that 4 inches is pretty adequate and does a pretty darn good job. I don't ever see sweating on the exterior of a cooler that I've built with 4 inches. And as a makeshift cooler, just last summer, I was using a cooler that I constructed just out of EPS foam with no cladding on the interior or exterior. Don't recommend that long term, but in the short term, it got us by. And even when it was very hot outside, we weren't seeing any sweating on the exterior of the cooler, which led me to the conclusion that it was doing an adequate job of insulating. What is the best way to cut the big foam boards? The best way I've found is to get a razor knife that extends out. So like the type of razor knife that snaps off to get a new pointy end on it. We don't snap them off, we just run them out 1.5 inches or so. and run that blade through. You don't have to cut all the way through, and then you can snap it. So similarly to how you cut sheetrock, if you score the paper, it is helpful to do it on both sides, although not necessary if you get a pretty good cut through it. And it can be tricky if your blade's not sharp as you're dragging it through the EPS. The little bits of EPS will start to follow the blade and get jammed up in there. So you really need a very sharp blade to accomplish it. I have in the past cut it with a circular saw, which works great, but makes a massive mess. And so I really don't do that anymore, just because it's a lot of cleanup when you're done. And if you're going to reduce the number of layers of EPS anywhere for affordability reasons, the ceiling is the place to do that. Again, remember that we have a big column of cold air that's sitting in there and pushing down, trying to move out all the cracks and through the walls in those spaces. So there's more benefit to insulation lower in the cooler, for instance, under the floor, than there is above the cooler. And like I mentioned in the video, if you think about a deep freezes are very, very low energy consumers as far as refrigeration equipment goes. And the reason for that is because you basically have a pool that's holding a still layer of cold air in it. And that's what we're trying to accomplish in our box here. Of course, every time we open the door, all that flows out, but that's the goal when it's sealed up, for it to hold air like that and hold the cold in like that. Yeah, once again, I have a note in here to remind you that the inside dimensions of your box will shrink when you hang the insulation on it. So when you build that structure, make sure that you are building it large enough that after you insulate it, you end up with the interior dimensions that you set out for. And that's something we should mention here too. I said that we want to design our spaces for the equipment that we use. And that is very much true on the interior and the layout, the interior dimensions and the layout in your walk-in cooler. So we use, as our harvest bins and as storage bins, we use attached lid totes, and we use totes that all have the same footprint. And so depending on what kinds of boxes or crates or whatever you use on your farm, you really want to think that through and think about how they layer up in your space as you fill that space up, because you can really get yourself in situations where you don't effectively utilize all of that space when you're at capacity. So a really good example of that is, as we were designing this, we shifted the door over far enough to allow the full width of one of those storage containers down that wall, because otherwise we wouldn't have been able to stack them on that wall without running into them or running our cart into them when we walked through that door. So laying out on that is definitely something to think about. Also, availability of freestanding shelving and the standard dimensions that it comes in can be something worth investigating before you do your layout. Rick is asking if we can share the cost of the walls and ceiling. Yeah, you bet. I've got a little budget here that I'll pull up, and we can take a quick peek at that. The overall build with this, including our refrigeration equipment, was around $3,000. You guys have that screen up now? Nope, not yet. You should see it now.
Yep, we can see it.
Great. So yeah, our 2x4 walls, around $200 worth of lumber, $120 worth of lumber in our ceiling, plywood decking on top, $90. Our joist hangers, pretty cheap there, $16. As you can see, our EPS represents a pretty high percentage of the overall project cost. Outside of the refrigeration equipment, it is by far the highest expense we have at $780. Great stuff. Of course, your mileage is going to vary on this. We used about 12 cans on this build at about $50, and boy, is that stuff handy for this. The FRP, which we haven't actually talked about yet, is also an expensive product at $30 a sheet. Although we don't use nearly as much of it as we do the EPS because it only goes on the final layer. Fasteners are something that often get left out of build budgets, so don't forget your fasteners. Caulk and glue, same story there. Oftentimes people forget about those things. $7 a tube on that Fuse It product, so $100 worth of caulk in there. We bought a pre-hung door, exterior steel clad door as our cooler door. Again, your mileage will vary there. If you build your own door, maybe out of the EPS with plywood cladding on it, that'd be a really well insulated door, but certainly a lot more work. Or if you're gonna find an actual cooler door. I've had good luck with that in the past, but I was not able to source any at an affordable price on this project. And then your CoolBot, which is the device that operates the air conditioner as a refrigeration unit, and then the window unit itself at around $600 or $700, depending on the size of unit you need. And as far as sizing that unit, storeitcold.com is CoolBot's website, and they have a really good chart on there that'll tell you what size air conditioner you need depending on how you've insulated your cooler and how large the cooler is. And actually, they have a lot of good resources in general. Just throw that out there. There's good design information on there, and definitely worth checking out. So, and for comparison, like I said, around $3,000 build on this. This is why we do it. A comparably sized commercial walk-in cooler is going to run you anywhere from $6,000 to $12,000, depending on where you source it. I do like the coolers that CoolBot is offering now, but there isn't a lot of customization available on them yet. I think they'll get there, but they're not there yet. Dwight is asking how many square feet this cooler was. Dwight, I believe this cooler was about, it was a little more than 10 feet by about 8 feet. And this budget that I have here would get you pretty close to a 12 by 8 cooler. Which would be a good dimension in order to make use of those pre-cut materials and minimize your cuts. Yeah, so armoring the walls, the FRP that we use. FRP is fiber reinforced panel, and it's the stuff you've probably seen on the interior of like kitchen walls, things like that. It's often used in commercial kitchens. It's a really durable product, very tough, really protects the foam from getting dinged and chipped and knocked around. It's also very easy to clean and wash down, so that's why we choose that product. It can be pinned to the wall with little plastic rivets, but we choose to glue it on because I think it holds up better. And that is a labor-intensive process. And we cut the FRP with either a circular saw or with shears. It will absolutely destroy a circular saw blade, so don't use a blade you care too much about on it. It also it's a fiberglass product, so take appropriate precautions with your eyes and your skin and your lungs if you're cutting it that way. My preferred method of cutting it is with shears, and you can cut it with a big pair of scissors. It cuts that way very, very nicely. but you'll sure wear yourself out on even a small cooler. A power shear is a very, very useful tool for a build of any size. Those can run on electricity or on air, depending on the shear, and they cut really nice clean lines in FRP. And then always dry fit it first before you put the glue on it. The glue is a product that is troweled onto the back of the on the FRP. And actually, I'm just realizing that's not in this budget, which it should be, because that is about $100 expense on a project like this. Yeah, it's sheared on with a well, the term is eluding me right now, but the jagged edged trowel, which gives an even distribution of the glue. So our process is we measure, we mark, we measure again, we cut, we dry fit it. So we put it against the wall and make sure it fits. Then we glue it, and then we put it on the wall permanently. I got a question here. Is thermal break insulation included here with EPS? Yes, it is. That included my floor insulation, I believe. Let's see, we had 26 sheets on that. You know, Nathan, I'm not positive it is. So in a cooler this size, that would have represented another 6 sheets. So again, that's a $180 expense that needs to be in there. Wouldn't guarantee that it's not in here, but I can't remember for sure. So don't want to lead you astray on it if it's not. So yeah, again, the purpose of that FRP is really just durability, and that's something that's very important to me in these types of projects. Again, because we're consuming resources in these projects, and particularly a product like the EPS that has significant environmental impact. We need to make sure that we get as much bang for our buck out of that embodied energy, and in this case, embodied pollution that we are committing to. So we want to make sure that we're gonna get as much mileage out of that as we can, and one way we can do that is to make sure that we make it quite durable. In this cooler, we didn't put FRP on the ceiling. I don't think it's necessary. The foam board paints up just fine. And the odds of it getting dinged up on the ceiling, of course, are much lower than on the walls. So I don't think it's worth armoring the ceiling with the FRP. It would look very nice, but outside of that, I don't think it's necessary. Sealing, again, just can't say it enough. We seal every crack as we go. Great stuff is indeed great for this. Every little crack that we come along, we do get that sealed up. And then for smaller seams, we can come back with silicone caulk and seal those. And of course, the silicone doesn't have much insulative value. We're just looking to seal for air movement there, because that cold air will find those little cracks. Mentioned the door a minute ago, but basically your easiest and best option is to find a real cooler door. If you can come across one used, it's not uncommon for the doors to survive even when panels don't, when something's getting torn down or whatever. So sometimes you can round one of those up, and they're great. They make a couple versions. One that actually sits in the wall, flush in the wall, and then another version that actually bolts onto the wall. And the ones that bolt on are a lot easier to utilize in home-built coolers. So that's the easiest option. The easy option is what we did here, which is a steel-clad exterior door. Clearly, a steel-clad exterior door that is, 1.5 inches thick does not have an R value of 25. So that is our weak link. But again, because it represents a fairly small square footage as compared to the remainder of the wall space, we're not too awful worried about it. The upside of a pre-hung door is that they seal really well, and that can be almost as good as a really well insulated door that doesn't seal as well. And it can be pretty tough to get a home built door to seal up as well. Home built doors, generally what they look like is a couple of layers of EPS laid up together and then clad in plywood to give them durability and structure. But again, can be tricky to seal up. One means of sealing those that I've found some success with over the years is just take a piece of EPDM rubber and hang it from both sides so it loops under the door and gives you a nice, somewhat loose seal, but something that seals easily against slightly uneven surfaces. So that's not a bad way to go there. And then we did also consider, and I think it would be of benefit, taking a sheet of EPS that is slightly smaller than your pre-hung door and just gluing it up to the door. So you're doubling up the thickness of that insulation. You just have to be aware that as that door swings, it needs to be a little bit smaller than your door so it doesn't catch on your jamb as it swings out. Dwight just said, what about adding a layer of EPS on the door interior? Yep, exactly. That would definitely get you there. And then Elizabeth's asking, where or what site is a good place to source used cooler parts? I have not found any sites that deal in used cooler parts. All I've been able to find as far as any kind of marketplace is new stuff. Really finding used stuff. Well, I say that. Sometimes you can find walk-in coolers, whole walk-in coolers usually, on Facebook Marketplace, on Craigslist. But those are oftentimes much larger than what we're actually looking for the farm. But that said, they can often be reconfigured into smaller coolers as needed. So that's a pretty good option. It's just very hit and miss as far as what's available, of course. So I haven't found any marketplace that specifically deals in used cooler parts. And then the mechanicals. So our options here are basically traditional refrigeration equipment. So like would be on a commercial walk-in cooler, or going the CoolBot route. The upside of commercial refrigeration equipment, and I know farmers that use both, and I know farmers who have used one and then moved to the other. The upside of commercial refrigeration equipment is that it's really robust and it has a ton of cooling power. So it can really chill down a lot of stuff very quickly. Generally, they have significantly more cooling power than you need to hold the temperature in one of these units. The downside of it is, as you might guess, the cost. Commercial refrigeration equipment is quite costly. And I think last time I shopped for a commercial refrigeration unit for a farm walk-in cooler, it was going to be around $3,000 for the refrigeration equipment. It can also have pretty high maintenance costs. They're notoriously unreliable, and so it can be something you chase. And it may be something that runs no problem for you for 10 years, or it may be something that you have to have somebody out to look at every year and a half or so. Just never know. So, and certainly the downside of that is that commercial refrigeration repair, when it happens, is definitely costly. And it's not usually something folks can handle on their own. The CoolBot route, if you don't know, CoolBot's a really cool company that started, I don't know, 15 years ago, something like that. They basically built a small microprocessor controlled unit that kind of hacks a window air conditioner. And the way that works is there's a room air temperature sensor on the CoolBot. There's a micro heater on the CoolBot, and then there's a fin temperature sensor on the CoolBot. And the fin sensor goes in the AC unit, and then you pull the sensor that is on the fins in the AC unit off of it, and you wrap it up in aluminum foil with the micro heater, and then you turn the air conditioner all the way up. And so what happens is when the room is not at your set point on the CoolBot, it turns that little micro heater on and tricks the air conditioner into thinking that the room temperature is below its set point, and it turns the air conditioner on. And then the fin sensor senses, because the air conditioner is not designed to be run that long without freezing up. It senses when the fins begin to freeze up, and it turns off the refrigeration unit, but keeps the fan running. And so it causes those fins to thaw very quickly. They're really cool units. They're very reliable. And when you have trouble with them, the CoolBot folks are awesome. They're really, really good customer service. Talk you through whatever you've got going on. CoolBots are compatible with both window units and a lot of mini splits. So the difference between those window units are what we've all seen. You stick in a window and it's all in one air conditioner. A mini split, on the other hand, is similar to a traditional or more common HVAC system that you find in a household. It's just on a smaller scale. So it has a line set that goes from the inside unit to the outside unit. And what that means is two things. One, you end up with a much smaller penetration in your insulated wall, only large enough for that line set to go through. But two, you most likely will require a professional installation for that unit. So the mini splits are also perhaps a bit more efficient, but they're also quite a lot more costly. And so I'm not sure that that efficiency gain is enough to overcome the added cost. I have not installed a mini split in any of the coolers I've put together so far, and that's always been because of the cost issue with them. Dwight was throwing out there that commercial equipment is designed to recover cooling very, very quickly and have much higher capacity than typically needed. That's absolutely correct. Yep, about 3 to 4 more times than you can get by with. And for that reason, window units and mini splits running on a CoolBot also have a much lower operating cost. They'll run much cheaper. CoolBot has some really great white papers on their website about exactly what that relationship looks like. But it has certainly been what we found to be the case. All that said, the biggest factor in how efficiently your cooler runs and what the cost of operating that cooler is how many times a day the door gets opened and closed. Fanning the door in a walk-in cooler is certainly rough on the refrigeration cost. It's necessary, but it's certainly something to take into consideration. And then we also do generally in our coolers we didn't at the setup there at Springfield Community Gardens, but oftentimes we'll build a cold side and a cool side. Cold side holds vegetables that hold well just above freezing. And the cool side holds vegetables that like to be around 50 degrees or so. And so on the cooler at Urban Roots, the way we handled this was we put a louver in the wall and a fan in the wall. And when the fan kicks on, the louver opens. The fan blows cold air from the cooler from the cold side into the cool side. And then the louver opens to allow that circulation to happen instead of pushing air out of the cool room and pulling warm air into the cold room. So easy way to do that. When we built the cooler at Red Barn in Bentonville, we didn't set it up that way. And in fact, we ran 2 window units in the cold side to get the capacity we wanted and the cooling capacity we wanted. And then ran a smaller unit in the cool side to manage that, and ran actually 3 cool bots on that setup. So, but for somebody who's bootstrapping like we were at Urban Roots, the louver and fan setup works pretty well. Rick threw out here that Graph auction has food service auctions, and they got a walk-in at Mount Vernon auction, but they had to remove it. So, and yeah, that's often the case when you can find a walk-in cooler. It may be in a building somebody has purchased and it's on you to install it. Although generally that's not too much of a trouble. The way they work is they have a cam in the wall that swings out and then locks in and pulls that wall section next to it tight. And you can get a Allen key in there to turn them. Although I can speak from experience that when they're rusted, you may be better off just taking a reciprocating saw right down between the panels and cutting those cam locks off. You can wrestle with them for a long time before they let go. I have a couple notes here to remind you that when you are calculating your costs and planning for your cooler, don't forget the fasteners, don't forget the glue. Try and think about every little thing. Good questions, Nate. Did I include the EPS for the floor in here? So we want to make sure that we're really thorough with our budget so we don't get surprises when we're in our build and see our costs go up. And then, yeah, total build cost around $3K on this cooler, if not ever so slightly more than that. So that is about all I've got for you guys. And that might be the closest I've ever come to an end time when I'm supposed to be ending. That said, if you guys have questions, I'm more than happy to answer them. So. Dwight's asking if we'd ever thought about building one in a container. Yeah, definitely. We've given quite a lot of consideration to that. And I think the real upside of that is that you can take it wherever you go. And certainly a container is an inexpensive way to build or to get a structure of that size. That temporary cooler I mentioned that was just built out of EPS was actually inside of a shipping container. That was a temporary scenario. Another option, my brother actually purchased an old reefer trailer, which when they're worn out can actually be purchased pretty inexpensively, and was using that as a cooler for a while. And in the interim period, when we had realized we needed cold storage on the farm, but before we had cold storage on the farm, we were actually using a reefer truck, just a small box truck, as our refrigeration space. Somebody's asking, how do we decide on the AC unit, BTUs, etc.? Your best resource for that is going to be the CoolBot website, and what they'll have for you there is a calculator. You put in what kind of insulation you've done, whether or not your pad is insulated. I think what your door is like, and then how large the cooler space is, and it will kick out what size refrigeration unit you need in order to meet those needs. And sometimes it'll even give you a couple of options. It'll say, you're kind of borderline. You may want to kick it up to a second unit in a space this size. And to be clear, CoolBot is doing everything from very small units intended for farms and even like home brewers, things like that, up to very large cooler spaces where they're running a bunch of 24,000 BTU units on CoolBots. So they're certainly modular and scalable, but yeah, as far as sizing, Coolbot's website, which is storeitcold.com, is a really great resource. They also have the best prices I've found on air conditioners. And not all air conditioners are compatible. They've done pretty extensive testing across brands. So they have good lists on there too, so you don't end up with one that doesn't work well with a Coolbot scenario. But LGs are the ones that I've found to be the best ones, most reliable ones that are compatible. And they have very good prices on them at storeitcold.com. Anita's asking if I feel like the fewer windows are better. Yes, absolutely. Yeah, you want to reduce windows as much as possible, preferably not have any in your cooler. And that is, again, an argument for the mini split. When you put your walk-in or your window unit into your walk-in, you're effectively cutting a huge hole in the wall that you just worked very hard to insulate. And so there is certainly some transfer that happens through that unit there. So even that, if it could be avoided, should be avoided. Anybody have any more questions? All right. Well, I'll go ahead and throw out there too my email address. I'm always up for talking with folks and being a resource for folks. So my email address is adam@urbanrootsfarm.com. So anytime you have questions, feel free to reach out, and I'll try my best to give you an answer that is meaningful. And Anita's saying, oh, Anita was asking about the windows because I mentioned I had windows. The windows are in the pack shed, not in the cooler at Urban Roots. And so, yeah, the windows are actually really beneficial, I think, in the pack shed. We like that natural light in there. It feels like a really good space to be in. Doesn't feel claustrophobic at all. And then, as I mentioned, they were designed with an overhang, so they're shaded. They allow light in, but they're shaded in the summer, so we don't get too warm in there. And then in the fall and winter time, when the sun's low, it passes that overhang and hits those windows and keeps us warm in the wintertime. So I encourage windows in the pack shed, but definitely not in the cooler. Sorry, I was confused about what you were asking there. Well, if you guys don't have any more questions, I'm just going to sit here in this room and talk to myself about walk-in coolers for a while longer, but you guys don't have to stick around for it.
Well, Adam, thank you so much for being here tonight and for talking with us. Super informational, a lot of good information that people can use. So